Very well. We are marching toward the conclusion of our study of infinite series. And to do that, we have to talk about series named for two rather famous mathematicians. One is Taylor and the other is Maclaurin. I believe it's Brooke Taylor and Colin Maclaurin that are responsible for what we're going to do today. So let's consider the following. Let's let f of x be a power series. If f of x is a power series, then f of x gets written as some constant times x minus the center, some constant times x minus the center squared, some constant times x minus the center cubed, and it just goes on and on and on. Well, let's take some derivatives. I mean, that's why we use power series. Power series are basically polynomials. Polynomials are easy to take derivatives of and integrals of. So let's do that. Derivative of a constant is 0. Derivative of this term is C1. And then there's 2C2 times x minus a, and then 3C3. Power goes down by 1. We could take the second derivative. The second derivative is 2c2 plus 2 comes down in front, right? And it just goes. And so then the third derivative, that's 0. The third derivative is 3 times 2c3. And this process goes on. But the punchline here is that for all n, the nth derivative evaluated at a is n factorial times c sub n. That's the key takeaway. The key takeaway, at x equals a, all of these terms are 0. At x equals a, all of these terms are 0. At x equals a, all of these terms are 0. So the first derivative is 1 times c1. The second derivative is 2 times c2. The third derivative is 3 factorial times c3, and so on. For all n, the nth derivative evaluated at a is n factorial times c sub n. But that's great, because that means if we want to know what the c sub n's are, this implies that the c sub n's are just the nth derivative of our function evaluated at a over n factorial. If this happens for all derivatives of all orders, then what we have is a Taylor series. And so we'll do the mathy thing and define it, and then talk a little bit about it. So we let f be a function with derivatives of all orders in other words, we can always take the next derivative on some interval containing a. Then the Taylor series generated by f at x equals a is, it's the sum, it's k goes from 0 to infinity, of the kth derivative at a over k factorial times x minus a to the k. Again, the c sub n's are nth derivative over n factorial, right? Why do we use k's here? Because in a moment, I'm going to use a k out here. So as a reminder, if k is 0, the 0th derivative is just the function value. If k is 1, we get the first derivative at a. 1 factorial is 1. times x minus a. If k is 2, this is the second derivative over 2 factorial times x minus a squared. If k is 3, this is the third derivative evaluated at a over 3 factorial times x minus a cubed. And this goes on and on for a while. There's an nth term. The nth term takes the nth derivative at a over n factorial times x minus a to the n, and it just keeps going. Again, when we're writing, when we show that things go on for a while, there's a plus, 3 dots and a plus. When we show that things go on forever, there's a plus and 3 dots. Time now for a side note. If a is 0, this is called a Maclaurin series. Okay? So a Taylor series is a special kind of power series. It's a power series where we can identify what the C sub n's are just by looking at derivatives. Okay? By way of example. Let's find the Taylor series generated by f of x equals 1 over x squared at a equals 2. So to generate a Taylor series, we have to know something about derivatives. We have to know, here's x to the negative 2. We have to know what a bunch of the derivatives are. Negative 2x to the negative 3. Negative 3 times negative 2 is 6. Negative 4 times 6 is negative 24, and so on, right? We have to know what those derivatives are. But we don't just have to know what those derivatives are. We have to know what those derivatives are at A, at A, at A. So we have to know what f of 2 is, what f prime of 2 is, what f double prime of 2 is, what f triple prime of 2 is, and so on. And it's not terribly difficult to figure out. This is 1/4. This is negative 2/8. This is 6/16. This is negative 24/32, and so on. So what happens? Well, we write the Taylor series. And the Taylor series says we take the function value, and then we add the derivative at a times x minus a, and then we add the second derivative over 2 factorial. So that's 6/16 divided by 2, x minus a squared. And then we do the third derivative, third derivative's negative, third derivative divided by 3 factorial. 3 factorial is 6. So divide this by 6. And then we try to decide if there is a pattern. Well, if there is a pattern, we try to express it here. And I think we can. I think there's a negative 1 to the n plus 1. I think there's an over 2 to the n plus 2. I think there's an x minus 2 to the n. Yeah. Oh, wait, nope, there's more. There's more. There's more. There's more. I'm just going to have to bring this into another spot. I'll bring this over here. So there's definitely negative 1 to a power. There's definitely something in a numerator and something in a denominator. And there's definitely x minus 2 to the n, and so on. So if n is 2, then the number here is 3. If n is 3, then the number here is 4. So this is probably n plus 1. If n is 3, this is 2 to the 5th. If n is 2, this is 2 to the 4th. If n is 1, this is 2 to the 3rd. This is 2 to the n plus 2. What's that power? Well, it's either n or n plus 1, depending on what happens in places like this. If n is 2, we need this to be positive. If n is 3, we need this to be negative. Negative 1 to the n does that. Right? Negative 1 to the n does that. Because if n is 2, we get a positive. If n is 3, we get a negative. And then it goes on forever and ever. So we generate a Taylor series by writing out a bunch of derivatives, figuring out what they are at A, and then using the formula. This is f of A, this is f prime of A times x minus A. This is f double prime of A over 2 factorial times x minus A squared, and so on. I will do a couple of more examples in another video for those folks who need to see this another time. All right? All right.